All right, this is cryptography. Lecture 3, we are covering section 1.3, which is on modular arithmetic. This is absolutely fundamental in mathematics, in number theory, and in cryptography. And if you are seeing this for the first time, then you really need to put in a lot of hours to understand what's going on. So the basic definition is as follows. Suppose we have an integer m, which is positive at least 1, which is called the modulus. And for any integers a and b in z, remember z is the set of all integers, positive, negative, and 0. For any integers a and b, we write a 3 lines b mod m if m divides the difference a minus b. And we read this as follows. A is congruent to b modulo m. So that's how we read this expression. And this is completely, absolutely fundamental in almost everything we do in this course. So for example, 7 is congruent to 1 mod 3 because the modulus 3 divides the difference, 7 minus 1, which is 6. 6 is 3 times 2. 3 divides 6, so 7 is congruent to 1 mod 3. 13 is congruent to minus 9 mod 11 because 11 divides 13 minus 9, which is 13 plus 9, which is 22. 11 divides 22, so 13 is congruent to minus 9 mod 11. $110 is congruent to 96 mod 7 because 110 minus 96, that's 14, is divisible by 7. It's 7 times 2. And minus 8 is congruent to minus 57 mod 7. Let's make it different numbers. Yeah, minus 8 because minus 8 minus 57 is 49, which is divisible by 7. 7 times 7. So this is the fundamental definition of congruence. And you need to spend a lot of time writing down pairs of numbers and moduli and seeing whether A is congruent to B mod M. You have to get used to this concept and to this notation. And this property of congruence has very nice attributes. So this in the book is proposition 1.13. So we have a modulus M, which is a positive integer. And we have various properties of congruences. So if A1 is congruent to A2 mod M, and B1 is congruent to B2 mod M. It's important this is the same modulus for both of these congruences. Then A1 plus B1 is congruent to A2 plus B2 mod M. And A1 minus B1 is congruent to A2 minus B2 mod M. And A1 times B1 is congruent to A2 times B2 mod M. So you can add, subtract, and multiply congruences. So let's just take an example. Let's say 11 is congruent to 5 mod 3. And minus 7 is congruent to 2 mod 3. Why are these true? 11 minus 5 is 6. 6 is divisible by 3. Minus 7 minus 2 is minus 9. Minus 9 is divisible by 3. So we have these two congruences. If we add them, what do we get? We get 11 minus 7 is 4. 5 plus 2 is 7. 4 is congruent to 7 mod 3, because 4 take away 7 is minus 3 is divisible by 3. If we subtract, 11 minus minus 7 is 18. 5 minus 2 is 3. And 18 is congruent to 3 mod 3, because 18 minus 3 is 15, and it's divisible by 3. And if we multiply them, what do we get? 11 times minus 7 is minus 77, congruent to 5 times 2. That's 10 mod 3. Is this true? Let's just check. Minus 77 minus 10 is minus 87. Is that divisible by 3? Yeah. That's 3 times minus 29. So this also checks. So this is an example of what we have in this proposition. Let me just prove the first statement. So A1 congruent to A2 mod M means or implies A1 minus A2 is divisible by M. It's equal to, let's say, M times X for some integer X. And if B1 is congruent to B2 mod M, that means B1 minus B2 is a multiple of M also. It's M times Y for some Y and Z. So if we add, we get A1 minus A2 plus B1 minus B2 is MX plus MY. On the right, MX plus MY, you can factor out the M is M times X plus Y. And on the left, I can rearrange this. This is A1 plus B1 minus A2 plus B2. So A1 plus B1 minus A2 plus B2 is a multiple of M. It's divisible by M. So we have, therefore, A1 plus B1 is congruent to A2 plus B2 mod M. So this is an example of a proof of this first statement. And it's an exercise, part of the homework, to prove these second two statements. So you have to know both the statement of the proposition and how to prove it. In mathematics, you don't know if it's true unless you have a proof. There's a second part to proposition 1.13, part B, which says that, so we're given an A and Z, and we have this modulus M greater than or equal to 1. There exists an integer B and Z such that AB is congruent to 1 mod M, if and only if the GCD of A and M is 1. So you're given A, and this is sort of like finding a multiplicative inverse. So in the numbers, if you were given a fraction, or even given A equals 2, and you find a fraction such that AB is 1. Well, if A is 2, B is a half. So this B is something like 1 over A. And these congruences modulo M. And the proposition says that given A, there's a B such that AB is 1, is congruent to 1 modulo M, if and only if A and M are relatively prime. So the proof goes as follows. If the GCD of A and M are relatively prime, then by what the book calls the extended Euclidean algorithm, there exist integers U and V such that AU plus B plus M V equals 1. You can always write the greatest common divisor of two numbers as an integral linear combination of them. So for A and M, a greatest common divisor 1, there exist integers U and V with AU plus MV equal to 1. Another way of saying that is that AU minus 1 is minus MV, M times minus V. So AU minus 1 is divisible by M. So AU is congruent to 1 mod M, and let B equal to U. I found an integer where AU is congruent to 1 mod M. So if A and M are relatively prime, there exists a B, which we can think of as a multiplicative inverse of A. And what about the converse? Conversely, if AB is congruent to 1 mod M, then AB minus 1 is divisible by M. So AB minus 1 is MC for some integer C. Another way of writing that is that AB minus MC is 1. And the only way this is possible is if the greatest common divisor of A and M is 1. So just any number that divides A and M would have to divide 1, so the only positive common divisor of A and M is 1. So this is really very important. If A is relatively prime to M, then it has a multiplicative inverse and conversely. And not only that, modulo M, this inverse B, is unique. So this is another part of the proposition. If AB is congruent to AB1, is congruent to 1 mod M, then in fact, B and B1 are congruent mod M. They can be different numbers, but they are congruent modulo M. And one way to see that is as follows. The number B1, this is all long congruence mod M. So B1 is congruent to B1 times 1. Just B1 times 1 is B1. But I can write B1, I can write 1 as A times B, because AB is congruent to 1 mod M, which is the same as B1A times B, and B1A is 1. This is 1 times B, which is B, so B1 is congruent to B mod M. So this is simply, if you like, a one-line proof, but each step requires several sentences of explanation. And this is because you can multiply any integer by 1 and it's the same integer. If AB is congruent to 1 mod M, then B1 times 1 is congruent to B1 times AB mod M. That's the multiplicativity of congruences. This is just associativity, but then B1A is 1, so we get B. So B1 is congruent to B mod M. And again, this is the sort of thing which, once you understand it, you can write it down in a couple of seconds, but it might take minutes or hours of thinking to understand it. If you remember the division algorithm, so this long division, for all integers, A and M, with M positive, if you divide, you can write A as M times a quotient plus R, with this integer R between 0 and M minus 1. Another way of writing this is that A minus R is MQ, which means A is congruent to R mod M. So every integer is congruent to some R, which is a non-negative integer strictly less than M. That means between 0 and M minus 1. And no two of these numbers can be congruent to each other because the difference is less than M. So it can't be divisible by M unless the difference is 0. I should also say something about fractions modulo M. So for example, suppose I take A equal to 7 and the modulus equal to 11. So 7 and 11 are relatively prime. So there's a number B where AB or 7B is congruent to 1 mod 11. So how do we find B? Well, for small numbers, I guess, trial and error works. And so if you just start going through the numbers, 0, 1, 2, 3, only go up to 10, eventually you'll find a solution to this congruence. And one solution is B congruent to 8 mod 11. because in this case, AB, which is 7 times 8, is 56. 56 is congruent to 1 mod 11. 56 minus 1 is 55, which is a multiple of 11. It's 11 times 5. So 7 times 8 is congruent to 1 mod 11. So another way of thinking of this is that in some sense, 8 is the same as a 7th mod 11. So if you wanted to try to write a fraction, mod 11, so long as the denominator is relatively prime to the modulus, like 5 over 7, what would that be mod 11? That's 5 times a 7th. A 7th is 8. This is 40. What is 40 mod 11? 7. Because 40 minus 7 is 33. It's 11 times 3. So we could say, with this understanding of what a fraction means when you're looking at a congruence mod n, 5/7 is the same as 7 mod 11. So this is a useful interpretation of fractions when we're dealing with moduli. So every integer a is congruent modulo m to exactly one integer in the set 0, 1, 2, 3, 4 up to m minus 1. We have m integers in this set. These are the possible remainders, all possible remainders, when you divide a number a by m. And so now we use this following notation. Z is the integers. This is red. Z mod mz. That this be the set of just these first m non-negative integers. And we think of these, when we think of these as elements of Z mod mz, and we call this the ring of integers modulo m. When we're looking at these as elements of this Z mod mz, we define addition, subtraction, and multiplication mod m. So for example, Z mod 5z is 0, 1, 2, 3, and 4. And in this set, 2 plus 4 is 6, which is congruent to 1 mod 5. So we would say 2 plus 4 is 1 in Z mod 5z. And in fact, we can make an addition table in Z mod 5z. So this is the addition table. Zero plus 0 is 0. 0 plus 1 is 1. In fact, adding 0 never changes anything. And this is 1 plus 0, 2 plus 0, 3 plus 0, and 4 plus 0. So just, this is the addition table. It's 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. What is 1 plus 4? It's 5, but modulo 5, it's 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, which is 0. 2 plus 4 is 6, which is 1 modulo 5. 3 plus 1 is 4. 3 plus 2 is 0. 3 plus 3 is 1. 3 plus 4 is 2. 4 plus 1 is 0. 4 plus 2 is 1. 4 plus 3 is 2, and 4 plus 4 is 3. So this is the addition table in Z mod 5Z. It tells you what you get when you add any two of these numbers. And you can also have a multiplication table. 0 times anything is 0, so I'll just put down the positive numbers, 1, 2, 3, and 4. This is the times table. Multiplication table. 1 times anything doesn't change. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. 1 times 4 is 4. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, but we're working modulo 5. So 6 is 1 mod 5. 2 times 4 is 8, which is the same as 3 mod 5. 3 times 1 is 3. 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4 modulo 5. 3 times 4 is 12. You divide by 5, you get a remainder of 2. 4 times 1 is 4. 4 times 2 is 8, which is 3 mod 5. 4 times 3 is 12, which is 2 mod 5. 4 times 4 is 16. You divide 16 by 5, you get a remainder of 1. So this is the multiplication table. Remember, in given m greater than or equal to 1, and any integer a, there exists a b such that ab is congruent to 1 modulo m, if and only if the greatest common divisor of a and m is 1. So it's useful to know what are the numbers relatively prime to m, the numbers for which a and m are relatively prime. And it only depends on what we would call the congruence class modulo m. So if a is congruent to a prime mod m, then the greatest common divisor of a and m is the same as the greatest common divisor of a prime and m. And the reason is that a congruent to a prime mod m implies that a minus a prime is some multiple of m times some number u. So an integer d divides a and m. It divides a and it divides m. It divides a prime, if and only if d divides a prime and m. So so the common divisors of a and m is exactly the same set of integers as the common divisors of a prime and m. And the largest element in that set is the GCD. So we let Z mod MZ star be the set of all A in Z mod MZ that are relatively prime to M. So Z mod 5Z star, that's, see, Z mod 5Z is 0, 1, 2, 3, 4. 0, 1, 2, 3, and 4. 0 and 5 have a common divisor, but 1, 2, 3, and 4, these are all relatively prime to 5. So Z mod 5Z star is these 4 numbers. It's the set of 4 numbers. What about Z mod 6Z star? Well, these are the numbers from 0 to 5 that are relatively prime to 6. And there are only 2 of them, 1 and 5. Because 0, 2, 3, and 4 have a common divisor with 6. What is Z mod 8Z star? These are the integers from 0 to 7 that are relatively prime to 8. Those are just the 4 odd integers. 1, 3, 5, and 7. And we let the capital Greek letter phi of M be the number of A in Z mod MZ star. It's the number of congruence classes that are relatively prime to M. And this is a very important function in cryptography. This is pronounced Euler. This is the Euler C function. This is pronounced like O-I-L-E-R, Euler. And phi is this Greek letter. So the Euler phi function is the number of elements in Z mod MZ relatively prime to M. So for example, how many elements in Z mod 5Z are relatively prime to M? There are 4 of them. So phi of 5 is equal to 4. If you look at the numbers in Z mod 6Z, only 2 are relatively prime to 6. So phi of 6 is equal to 2. If you look at the 8 numbers in Z mod 8Z, exactly 4 of them are relatively prime to 8. So phi of 8 is equal to 4, and so on. This is the Euler phi function, which is extremely important in cryptography. In fact, we'll see in a month, which means next week, that one of the most important cryptographic schemes, something called the Rsa Crypto System, which is the basis of all international internet commerce. It's based on congruences and the Euler C function. When I say that all of internet commerce is based on this algorithm, this crypto system, what I mean is the following. If you want to buy something on Amazon, you go to Amazon, you click, and you put in your credit card. And the credit card is sent to Amazon, and it debits your credit card. If someone intercepts the transmission between you and Amazon, they have your credit card number, and they can use it, and you're not very happy. So you won't use Amazon again. So when you buy something on Amazon, your computer, and you enter your credit card number, your computer doesn't transmit your credit card number. It encrypts it, it encodes it. It uses some secret method to code your credit card number. That is what is sent to Amazon. Amazon gets it, decrypts it, decodes it, charges your credit card, and sends you your purchase. And anyone who intercepts the transmission between you and Amazon, they don't have your credit card number in plain text form, in a form they can read. They have your credit card number encrypted. And if the encryption system is reliable, they cannot decrypt, they cannot decode the number and steal your money. So what makes commerce possible in the internet is a reliable encryption scheme. And that the encryption scheme that's used is called, it's named after its three discoverers, Shamir and Edelman, RSA, there's their initials. And this Rsa Crypticism is what Amazon uses. And it's based on congruences. And it involves the process of taking a number and raising it to a very high power and then reducing it modulo M. So what is called the Rsa Crypto System, which is discussed in chapter 3 of the text, uses taking a number G, raising it to a power A, and looking at its congruence class, modulo some number capital N. So if we want to use G to the A congruent to R mod N, so where R is in Z mod NZ, which is the set of numbers just from 0 to capital N minus 1. So for example, suppose we want to compute 3 to the 7th mod 5. So 3 is congruent to 3 mod 5. How do we multiply by 3? 3 squared is 9, is 4 mod 5. Multiply 3 again. 3 cubed is 3 times 4, is 12, is 2 mod 5. 3 to the 4th is 3 times 3 cubed. That's 3 times 2. That's 6. That's 1 mod 5. 3 to the 5th is 3 times 3 to the 4th. That's 3 times 1. That's 3 mod 5. 3 to the 6th is 3 times 3 to the 5th. 3 to the 5th is 3, so that's 3 times 3, that's 9, which is 4 mod 5. And 3 to the 7th is 3 times 3 to the 6th, which is 3 times 4, which is 12, which is 2 mod 5. So 3 to the 7th is congruent to 2 mod 5. And I had to do how many multiplications? 1, 2, 3, 4, 5, 6. I started with 3, and then I multiplied by 3 6 more times to get the answer. Well, that wasn't so bad, but suppose I had something more interesting. Suppose I want to calculate, let's say, 3 to the 218th power mod 1,000. So this would require 217 multiplications, doing it like this. And after each multiplication, I would have to reduce mod 1,000. That's more work. In computer science, one worries about not just whether a computer program will run, but how long it will take. Will it take 1 millisecond, 2 hours, or 1,000 years? And raising a number to a power of 3 to 218, that's only 217 multiplications, not so bad. That's not so bad, but you can imagine if you had a really big number up there, there'd be a lot of multiplications. So we want to find a quicker way. That means a more efficient algorithm to compute powers. of a number. And one method, one algorithm, is to take your exponent and write it as a sum of powers of 2. So you know every integer is uniquely a sum of distinct powers of 2. So what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, 128, 256, and so forth. If I want to write 218 as a sum of powers of 2, I'll do it the simplest way. I'll pick the largest power of 2 that I can. 256 is too big, but 128 is okay. This is 128 plus 90. And 90, the largest power of 2, no bigger than 90, is 64. So this is 90 plus, I think, 26. And 26 is 16 plus 10. And 10 is 8 plus 2. So I've written 218 as a sum of powers of 2. 218, this is 2 to the first power. 8 is 2 cubed. 16 is 2 to the fourth. 64 is 2 to the sixth. And 128 is 2 to the seventh. So this is what is called the binary representation of 218. And I'm going to show you how we can use this binary representation to compute 3 to the power 218 mod 1,000 without 217 different multiplications. Okay, let me just write this down again at the top of the page here. 218 is 2 to the first power plus 2 cubed plus 2 to the fourth plus 2 to the sixth plus 2 to the seventh. Now I want to observe the following. If I have 3 to the power 2 to the k, and I square it, I multiply it by itself, I get 3 to the power 2 to the k times 2, or 3 to the power 2 to the k plus 1. So if I want to go from 3 to a power of 2 to 3 to the next higher power of 2, that only takes one multiplication. So let me show you how I can fairly quickly compute 3 to the power 218 modulo 1,000. So I'm going to make a table. For each power I, I'm going to write 3 to the I mod 1,000. And I only need to know this up to the 7th power. So 3 to the 0th power is 1. Sorry, this is going to be 3 to the power 2 to the I. So 2 to the 0 is 1. 3 to the first power is 3. If I want to get 3 to the 3 squared, it's 3 to the power 2 to the 1, 3 to the power 2. I just square 3, I get 9. If I want to get the next higher power of 2, 3 to the 2 squared, that's 3 squared squared 9 times 9 is 81. If I want to get 3 to the power 2 cubed, I square 81. What is 81 squared? By the way, in this course, you are definitely allowed to use a calculator or a computer. And everyone has a computer, obviously, or you couldn't be taking this course. And there's a calculator on your computer. If you don't know any computer language, there's always a calculator on your computer, or you can go to Staples and for probably less than $5 buy a cheap little calculator, which is all you need. What is 81 squared? 6,561. What is this modulo 1,000? 561. So 3 to the 2 cubed mod 1,000 is 561. What is 3? So this is 3 to the 2 cubed. 3 2 to the 4th is 3 to the 2 cubed squared. Modulo 1,000, 3 to the 2 cubed is 561 squared. This is mod 1,000. What is 561 squared? According to my calculator, this is 314,721. Which is congruent to 721 mod 1,000. 3 to the 2 to the 5th is 3 to the 2 to the 4th squared. That's 721 squared. My calculator says that 721 squared is 519,841, which is congruent to 841 mod 1,000. 3 to the 2 to the 6th is 3 to the 2 to the 5th squared. That's congruent to 841 squared. 841 is 707,281, which is congruent to 281 mod 1,000. And finally, 3 to the 2 to the 7th is 3 to the 2 to the 6th squared. That's 281 squared. That's 78,961, which is congruent to 961 mod 1,000. So we have this little table, and it only took how many multiplications? 7. Start with 3, square it, square it, square it, square it. 1, 2, 3, 4, 5, 6, 7 squares. And we were done. And now we want to solve our problem. What was our problem? Compute 3 to the power 218 mod 1,000. So let's do it right now. 3 to the 218. What is 218? It's 2 to the 1st plus 2 cubed plus 2 to the 4th plus 2 to the 6th plus 2 to the 7th. That's 3 squared, 3 times 2 cubed, 3 times 2 to the 4th, 3 times 2 to the 6th, 3 times 2 to the 7th, which by the rules of exponents. What are these numbers modulo 1,000? 81, 561, 721, 281, 961. So now we have to do how many more multiplications? 1, 2, 3, 4. So let me do those multiplications. I'm using my calculator. 81 times 561 times 721 times 281 times 961. You might get a number which is actually too big for my calculator. It wouldn't be too big for my computer. Let me do this a little bit more carefully. Suppose I take 81 times 561 and I get something with modulo 1000 is 441. Then I multiply that by 721. And I get a number which modulo 1000 is 961. If I take 961 and multiply it by 281, I get a number which modulo 1000 is 41. And 41 times 961 gives me a number which I don't like. So I'm going to double check this. So 3 squared is 81. 3 to the 2 cubed is 561. 3 times 2 to the 4th is 721. Oh, it's 3 times 2 to the 6th. Yeah, that's right. 3 times 2 to the 6th is 281. And 3 times and 3 to and times 3 to 2 to the 7th is 961. So I need to multiply these numbers together and reduce it modulo 1000. Oops, oh, sorry, here's my mistake. It was 3 to the 2 to the first power. 3 times 2 to the first power is 9. It's not 81. It should be the 9 here. That's correct. This is 3 squared. So now, let me do it again carefully. So 9 times 561 times 721. That's a number which, when I reduce it modulo 1000, is 329. 329 times 281. When I reduce it to 1000, is 449. 449 times 961. When I reduce it by 1000, it's 489. So 3 to the 218 power is congruent to 489 mod 1000. And if you count the number of multiplications, the number of computer operations I needed to get this result, I didn't have to multiply 3 by itself 218 times. I did it roughly 7 times plus another 6 or 7 multiplications, maybe for each of them, at most 1 reduction mod 1000. Maybe it took 10 or 11 steps, a lot less than 218. So this algorithm for fast powering is extremely useful. And one uses it in computer programming all the time. And one uses it, therefore, in cryptography all the time. Okay, so this is section 1.3. You really do need to spend a lot of time working on this and understanding it, because it is going to be fundamental to everything that we do. And please make sure you spend as much time as you can working on the homework problems involving congruences. That is it.